I wanted to start this lesson out by reviewing one question from section 1.7 and then one from 1.8. So again, pause the video whenever you feel it's necessary to copy a problem down or keep up with the notes. All right, so here we want to prove the statement using the epsilon delta definition of a limit. So we need to go back to just the general format of a limit, which is the limit as x approaches a of f of x is equal to L to help us put our pieces together here. So anytime there's a proof or a problem we want to start involving this definition, it always starts with that we're given an epsilon greater than 0. We must find a delta greater than 0 such that if, now we start with the delta inequality statement, that x minus a, in this case, a is the 2, so x minus 2 in the absolute value is less than delta. Then we have the epsilon inequality statement, which is the absolute value of f of x, which is the 14x minus, or 14 minus 5x, minus our limit L, which is the 4. And then that is going to be less than epsilon. So what we start with next, so this is step 1 here. Step 2 is to start with the epsilon inequality and just simplify it, because what's inside is we want to get it to look like x minus 2. So we'll see if that happens. So we'll have absolute value of 14 minus 5x minus 4 less than epsilon. Combining like terms here, we're going to get a 10 minus 5x. Now remember, one way to do this, we don't have fractions, so we don't have to worry about that, is we want to try to factor. But if you notice, I wanted to have the x term first. So because this is kind of backwards, let's go ahead and switch the terms. A negative 5x plus 10. And then here, we actually are going to factor out a negative 5 times x, and careful with the signs, minus 2. If we double check this, distribute back, we'll get a negative 5x plus 10. So that's less than epsilon. Then we'll use properties of absolute value. So I could separate this as absolute value of negative 5 times the absolute value of x minus 2 is less than epsilon. So this will become a 5, positive 5, times the absolute value of x minus 2 is less than epsilon. So now absolute value of x minus 2 is less than epsilon over 5. So we got that x minus 2 inside, which is what we wanted. So now step 3, we'll say, so, or rather, if we choose delta to equal this epsilon over 5, then this statement is true. The absolute value of x minus 2 is less than delta, because we're just replacing down here the epsilon over 5. And then this statement here implies that that limit, 14 minus 5x minus 4, or the epsilon inequality rather, the limit, or the function minus the limit here, is less than epsilon. Then we're taking statement 3 here to say, thus, because this holds, then it's saying the limit as x approaches 2 of 14 minus 5x is in fact equal to 4 by the definition of a limit. All right, so there's another example from section 1.7. All right, the next one is from 1.8, dealing with continuity. Again, pause the video to copy this down. Here we want to show that f of x, which is a piecewise function, is continuous at x equals 3 using the definition of continuity. So if you go back to your notes, there's 3 requirements that must be met for this, this definition to say that f of x is continuous at the certain x value. So the first step is we want to show that f of c exists. Now c is just this special x value here. So here we would say f of c in this case is equal to f of 3. And if we go back up to our piecewise function, when x is exactly 3 is right here, and the output is 23. So that task is done. F of c does exist because f of c is f of 3 in this case, which is 23. The second thing we want to show is that the limit as x approaches c of f of x also exists. So in this case, we want to show the limit as x approaches 3 of f of x exists. Well, because this is a piecewise function, we have to show the two one-sided limits. So that's what I'm going to start with. The limit as x approaches 3 from the left of f of x. So if I go back up to my piecewise function, if we're approaching 3 from the left, we're using this inequality, so we're using this expression. So we could just do direct substitution. 3 times 3 squared minus 4. 3 squared is 9 times 3 is 27 minus 4 is 23. Then we show the limit as x approaches 3 from the right of f of x. So we go and we use this bottom one right here. As x is greater than 3, we're going to use the 5x plus 8. So this becomes 5 times 3, which is 15, plus 8 is 23. So these two values are equal. Therefore, the limit as x approaches 3 of f of x exists, and it's equal to 23. And that's what the third step is. The third step is that f of c must equal the limit as x approaches c of f of x. So in this particular problem, it's f of 3 needs to equal the limit as x approaches 3 of f of x. And they do, because f of 3 is 23, the limit is 23, so that's good. So therefore, we say f of x is continuous at x equals 3. And this was like that first case that we looked at for limits. So if we have some function, so let's say we're looking at, and again, I'm not going to draw this one in particular, but if we had f of 3 was equal to 23, we have a point right here, and then our graph goes right through it. So something like this. So that just means our left-hand limit is equal to our right-hand limit, and the point exists right there. And that altogether we would draw without picking our pencil up off of our paper. So this would be continuous. So again, the definition of continuity holds with this particular problem. And by showing those 3 steps, we were able to conclude that at the very end. All right, so section 2.1 deals with derivatives and rates of change. Now back in section 1.4, we looked at rates of change from the table standpoint, which you guys saw was a little bit lengthy. We mostly had to use our calculator when the numbers weren't nice enough. So the material we're going to do today, the types of problems we're going to do today, are still going to be lengthier, but they're not tables. They're going to rely on algebra. Now, eventually, we'll get away from this lengthy process and get into the shortcut methods, but we have to take a look today at the definition of a derivative. Now, there's 2 examples I'm going to show you here, 2 formulas we can use. This first one is going to be the easier algebra to use. I'll show you the other one, but I'm not going to use it just yet. We might come back to it in a couple sections, but go ahead, make a coordinate plane here and just draw some curve that maybe looks like this. Call this f of x. And right along the x-axis, let's call this a. And then a little bit to the right, let's say it's a plus h units. Let's put a point here right above a and then right above a plus h. So if this is the curve y equals f of x, the ordered pair here would be a comma f of a. And then right here would be a plus h comma f of a plus h. Now I showed this to you before in class, but to come up with a secant line, so let's go ahead and draw a secant line going through these 2 points. So the slope of the secant line would then just be my y2, which is f of a plus h, minus my y1, which is f of a, all over my x2, which is a plus h, minus my x1, which is a. So this becomes f of a plus h minus f of a all over h. And that's where we're getting that difference quotient from. Now this is also known as the average rate of change, which you use plenty of times, also known as the average velocity. And we see those that question come up quite a bit in our past homework and sections that we've been looking at. Now let's say I wanted to find the slope of a tangent line right here at A. So this would be an example of my tangent line drawn in there where it only touches or intersects the curve at one point. So this is my tangent line. So that's going to happen if I start to move this point here closer, or a plus h is getting closer to A. So if that's getting closer to A, that means my H is decreasing. So this will happen, the distance decreases, the distance between decreases as H approaches 0, as H keeps getting smaller and smaller. So now the slope of my tangent line, I'm going to put that in as a limit because H is getting smaller and smaller. So it's just going to be the limit as H approaches 0 of this difference quotient. So f of A plus H minus f of A all over H. This is known as the instantaneous, I'm going to abbreviate it this way, instantaneous rate of change, also known as the instantaneous velocity. So now we don't have to go through a table and start calculating all of these slopes to see what they're approaching here. Now here's a new notation though. This is also equal to f prime of A. This is the notation for a derivative. So this means it's the slope of a curve at x equals A. It's also the slope of a curve. That phrase means the slope of the tangent line at x equals A. And it also means the derivative of a function. So we'll say derivative of f of x at a specific x value at x equals A. So all of these mean the same thing. Instantaneous rate of change, instantaneous velocity, the definition of derivative that's at the very top, f prime of A. All of these are synonymous with the slope of a tangent line at a specific x value. All right, so I'm going to redraw this now, but instead of using A and A plus H, the formula will look a little simpler, but the work involved could be more complicated. You get into more complicated factoring, which isn't pleasant to go through. So that's why I said I'm going to keep using the formula on the previous page. So let's call this first point A again, but instead of A plus H, let's just call the second point X. Again, this is y equals f of x. So my first point here stays the same, f for A and f of A. And then this point here would just be x and f of x. So now to draw my secant line, again, a line that goes through 2 points, slope of my secant line would again be my y2, so this becomes f of x minus y1, which is f of A, all over x2, which is x, minus x1, which is A. So it looks a lot easier. We don't have a binomial that we're trying to substitute this in. And again, this is the average velocity, average rate of change. But now to draw in the tangent line at A, this would now become, or I could write it as f prime of A. It's still going to be the limit, but there's no h involved, so I'm not going to say h approaches 0. And here, x is just going to kind of move backwards and get closer and closer to A. So it's as x is approaching A. So the limit as x approaches A of f of x minus f of A over x minus A. So instead of just having a monomial in our denominator, now we have the binomial. And that's what can cause more complicated algebra factoring to go through this. But I wanted to show you there's as many ways as you want to call the x values of these 2 points. You can set this up. We could even use like x and delta x, and that's even more complicated notation. But just to show you an alternative, and we may encounter this down the road. But for right now, like I said, I want to go back and keep using this version of it. We're familiar with it so far from what we've done in previous sections. We're going to stay with it. All right, so we're going to do several examples using that definition of a derivative. So consider the curve y equals x minus 3x cubed. We want to find the slope of the tangent line to the curve at 1, negative 2. And what's going to be helpful here is because I could ask for multiple points. So I don't want to use the specific numbers right away. I want to find the general one. I want to find f prime of A first. Then once I do that, I'll have a general derivative for the derivative at any A value. And then I'm able to substitute that in rather than finding it for 5 different points going through this process, this long process. 5 different times. So f prime of a, which is the slope of the tangent line, which is the limit as h approaches 0 of f of a plus h minus f of a all over h. So this is my function I'm going to use. So this becomes a limit. Notice where I put the equal sign. I never put an equal sign between the limit and the function, this difference quotient here. It's always equals the limit. So I'm going to have a plus h is going to go in first here. So I have a plus h going in for the x. Minus 3 times the quantity a plus h cubed. And yes, that will be a bit to write out, but we'll go through it. And then minus, now because this is a binomial, I want to put it in brackets, a minus 3a cubed. Technically, yes, you can leave the a's as x's, but it's showing us at a specific x value, which is a. And then this is all over h. So what we first need to do is expand this. So off to this side, let's go ahead and do it. It means a plus h being multiplied 3 times. So I'm going to first multiply the last two. So this will become a plus h. This will give me an a squared plus ah, so 2ah plus h squared. Carefully go through and distribute here. So I'm going to get a cubed. I'm just distributing the a first throughout, plus 2a squared h plus ah squared. Then I'm going to go through and distribute the h, but I'll write the a first, a squared h, then plus 2ah squared plus h cubed. So combining like terms, I have a 2a squared h plus a 1a squared h, so I get a cubed plus 3a squared h. Then I have an ah squared plus 2ah squared, so plus 3ah squared, then plus h cubed. So that's what I need to write out here. All right, so we'll have limit as h approaches 0. We have a plus h. Still leave this minus 3, so what I just found I'm putting in brackets. A cubed plus 3a squared h plus 3ah squared plus h cubed. Distribute this negative sign carefully. Let me write that better. So we're going to have a minus a plus 3a cubed. Now what you guys have seen throughout these problems is stuff starts to cancel, but I need to close my bracket after this and then over h. So I have to distribute the negative 3 next before I start to cancel things out. But notice this first a here and then this minus a here is going to cancel out. But let's go through this and distribute that negative 3. So I get the limit as h approaches 0 of a plus h minus 3a cubed minus 9a squared h minus another 9ah squared minus 3h cubed minus a plus 3a cubed all over h. All right, so now this a crosses out with this a. 3a cubed here crosses out with, or negative 3a cubed crosses out with a positive 3a cubed. And that looks like everything. Now imagine what I have crossed out in blue is just completely gone, just to save a step. I can go through and divide this h, all of these terms here, by this h here, and that's going to get rid of that denominator. So let's go through that. So I still have the limit notation. So h divided by h is 1. Minus 9a squared h divided by h is minus 9a squared. Minus 9ah squared, divide that by h, is minus 9ah. And then minus 3h cubed, divide that by h, minus 3h squared. Now what's going to happen is h is going to 0. So any term that has an h in it just becomes a 0. And 0 times anything, because h is 0, 0 times anything is going to be 0. So this goes away, turns to 0. This goes away, turns to 0. I no longer need the limit notation because I used h going to 0. I get 1 minus 9a squared. So this is f prime of a, or it's also the slope of our tangent line. So we found it at any point a. We wanted it at the point, what was it, 1, negative 2? 1, negative 2. So at 1, negative 2, f of a, or f prime of a rather, becomes f prime of our x value of 1. So now I substitute the 1 in here. 1 minus 9 times 1 squared becomes 1 minus 9, or negative 8. So if we were to graph that curve and then plot the point 1, negative 2 and draw a tangent line through it, that tangent line would have a slope of negative 8. But yes, we did all this work just to find that value. Is very important. It's a little bit of work because we're using the definition of a derivative. Let's go ahead with another example. Here we want to find the equation of a line. So not only the slope of the tangent line, but the entire equation of the line tangent to the curve, y equals radical x minus 6 at the point, let's say 4, negative 4. All right, so again, our first step to find the slope of the tangent line, which is equal to f prime of a, which is equal to, I would always recommend writing this out. The more you write these three equivalences out, the easier it's going to become when you're asked different questions. So it's the limit as h approaches 0 of f of a plus h minus f of a all over h. So here's my function. So next we get the limit as h approaches 0. So here I'm going to have square root of x is now the a plus h minus 6 minus f of a becomes radical a minus 6. And yes, I have to put those in brackets or parentheses, all over h. So it doesn't expand as crazy as the last one did. We have a limit as h approaches 0, radical a plus h minus 6 minus radical a, but then a plus 6. So you see what's going to happen next. These 6's are gone. I still have to write what's left over. I can't divide both of these by h like I was able to in the last part. So I still get the limit as h approaches 0, radical a plus h minus radical a all over h. Okay, still can't do direct substitution, so what do you guys think we need to do to proceed? It's with that numerator. We've got radicals in the numerator, so we must rationalize it. So I need to multiply the top by the conjugate here, radical a plus h plus radical a, all over radical a plus h plus radical a. Carefully do this. So we will have, again, keep the limit with it. Limit as h approaches 0. Radical a plus h times itself is a plus h. I chose the conjugate because my outside terms and my inside terms are opposite, so they cancel. And then I'll have a minus radical a times itself is a, and you see what's going to happen with those a's, all over h times the quantity radical a plus h plus radical a. So yes, now these a's cancel. I'm still going to write out the next step, just to show you, because we don't just have a single h in the denominator. So I'm going to get h over h times this quantity, and now you're going to see those h's divide out. So these divide out, turn into 1. So now I'm left with the limit as h approaches 0 of 1 over radical a plus h plus radical a. Now I can substitute in 0 for h. So this goes to 0. I no longer need the limit notation because I used h as 0, or 0 for h. So I'm going to get 1 over radical a plus radical a. And I can combine that into 1 over 2 radical a. So again, this is f prime of a, or the slope of our tangent line. All right, so now we're at the point 4, negative 4. So this is the slope of the tangent line at any point a. Here, a is 4. So now f prime of 4 becomes 1 over 2 times radical 4, 1 over 2 times 2, so we get 1/4. So this is the slope of our tangent line. And we're at this point. So we have our slope, we have a point. To write our equation, we're going to use point-slope form, which, if you recall, y minus y1 equals m times x minus x1. So this becomes, this is my y1, this is my x1. So we're going to get y minus a negative 4 equals our slope of 1/4 times x minus 4. So this becomes y plus 4 equals 1/4 x minus 1. Subtract 4, so we're going to get y equals 1/4 x minus 5 as our equation. And I just want to show you how you could check this on a calculator as well. So I went ahead and I graphed y equals radical x minus 6. And then I want to type in, we had 1/4 x minus 5. So we could see our line is tangent. Let's go to graph trace at 4. We can see right here at this point, let's see if I can move these out of the way. All right. Let me go back and plot this point here, right here. All right, so we see the point, 4, -4, that's where it's tangent. And we see our tangent line. When I graphed this, we did have the right equation because this is exactly where that red line is tangent to our curve at y equals radical x minus 6. All right, a lot of times calculus and physics can go over the same problems, so especially when we're dealing with velocity, displacement, acceleration eventually, and position, we use calculus to help us determine the physics side of things. So pause the video, go ahead and write this little word problem out. So if a rock is thrown upward on Mars with a velocity of 12 meters per second, its height in meters after t seconds is given by this function. H of t, or just h, is equal to 12t minus 1.86 t squared. Find the velocity of the rock when t is equal to a. All right, now it doesn't specify which type of velocity. So when it doesn't, this means instantaneous velocity. If not, it's clearly going to say average velocity. So we want to find the instantaneous velocity of the rock when t is equal to a. So that means we want to find f prime of a. Because remember, that's the same thing as the instantaneous velocity. And that's the same formula we just used on the last two problems. That's the limit as h approaches 0 of f of a plus h minus f of a all over h. So let's apply it to this problem. Our function again is right up here. So we're going to have the limit as h approaches 0 of 12, and then we're going to replace the t here with the a plus h first. So 12 times a plus h minus 1.86 times a plus h squared. So that's just filling in this first part. Minus f of a, so we're going to have 12a minus 1.86 a squared. Now, I know we have a decimal here, so if you need to use a calculator, that's fine. Pause the video and work the rest of this out and see if you guys come up with the same thing I do. So I'll give you a few seconds to do that. But again, pause the video and then resume playing. All right, so continuing here, we'll get a 12a plus 12h minus, we have to square the a plus h first, so it's 1.86. This will become a squared plus 2ah plus h squared. Then we'll have minus 12a and then plus 1.86 a squared all over h. All right, so this becomes limit as h approaches 0. We'll just distribute that negative 1.86. So we get 12a plus 12h minus 1.86 a squared minus, if we double 1.86, we should get 3.72 ah minus 1.86 h squared minus 12a plus 1.86 a squared all over h. Things should start to cancel now. So if you notice 1.86 a squared here with a negative 1.86 a squared there, minus a 12a plus a 12a, and that looks like it's it. So we get the limit as h approaches 0 of 12h minus 3.72 ah minus 1.86 h squared all over h. So substituting in, actually before we do that, divide everything by h, so we get the limit as h approaches 0 of 12 minus 3.72a minus 1.86 h. Now h can go to 0, which means this last term here becomes 0 when h is 0. We no longer need the limit notation, so it's just 12 minus 3.72a. So this is f prime of a, our derivative, or the instantaneous velocity when t equals a. All right, so that was just question 1. Find the velocity of the rock when t equals a. So we did that. Part B, find the velocity at or after. You're going to either see it phrased two ways. Find the velocity at t equals 2 seconds or after t equals 2 seconds. It still means the instantaneous, that instant when t equals 2. or in this case, A is our special number here, so 2 seconds. So going back to f prime of A was equal to 12 minus 3.72 A. So now we get f prime of 2 just becomes 12 minus 3.72 times 2. Go ahead and calculate that. All right, so this should give us 12 minus 7.44, which then we get 4.56. So going back to the beginning of the problem, velocity is 12 meters per second. So that's the initial, and then we're seeing its height after t seconds given by this equation here. So again, we're in meters per second. So velocity is always a rate per time, so meters per second here. For part C, when will the rock hit the surface? Well, right now this has nothing to do with velocity, it's just position. So we hit the surface, the rock's going to hit the surface when the height is what, guys? There is no height, right? When the height equals 0. So the height was given to us, that was the 12t minus 1.86 t squared. So we want to set this equal to 0. So 0 is just going to equal 12t minus 1.86 t squared, and we'll solve this. It's a quadratic, so we'll factor out a t, and we'll get 12 minus 1.86 t. We'll set both of these equal to 0. So t equals 0 means at the beginning, right here, our rock was at a position of 0. Then it went up, tracking its height versus its time. We do get, it's a quadratic, so we get a parabola that opens down. So right over here is when it hits the ground again. So we would set 12 minus 1.86 t equal to 0. So 12 would equal 1.86 t. Now just divide 12 by 1.86. And we'll round to just 3 decimal places. So t is approximately 6.452 seconds. So it's in the air for a total of about almost 6.5 seconds here. But again, it kind of takes this parabolic path, but this is just tracking height versus time. So right over here would be that 6.452 seconds is when it came back down. All right, D, with what velocity will the rock hit the surface? So this means, what is the velocity at when it comes back down to hit the surface at t equals that 6.452. So if you remember, f prime of A was equal to 12 minus 3.72a. So now we want f prime of 6.452. So go ahead and calculate that. And here we get a negative 12.001 meters per second. So does it make sense for velocity to be negative? And yes, it actually does. Because when velocity is positive, it really means, and we're going to explore this so many more times throughout this course, velocity being positive just means direction. So this means our particle is going up in a positive direction. It's moving up, to the right, or forward. When velocity is negative, it just means the particle is moving down, left, or backwards. Now, when velocity is 0, that's actually when we're changing direction. So we'll take many, many more examples of working with velocity here. But all this means the velocity is negative because our rock was coming back down when it hit the ground. It was the direction it was traveling in at that instant. All right, something else we do with particles is displacement. Now, displacement is just change in position. So, for instance, if we started, and a number line is the easiest way to look at this. So let's say on the first part of our trip, we move maybe 5 units to the right. Then on the second part of our trip, we move maybe 8 units back. So let's say we go 8 left, which puts us at a -3, and we stop right here. Our displacement, I'm going to abbreviate like this, is actually only 3. It's how far we were from our original position. So our displacement is right here. We are just 3 units from where we started. It doesn't matter our total trip, it just matters our final destination compared to our initial spot where we started. So our displacement is just the change in position. Now velocity is the rate of change in position. So the notation we use here, displacement is just our change in s, that's delta s, change in position, where s or x sometimes is our change in position, or representing our position. So velocity, looking at this is just the rate of change in position, or it's a derivative of the position function. And we'll do more work with this throughout this chapter. All right, so here we're looking at the displacement in meters of a particle moving in a straight line is given by s is equal to t squared minus 4t plus 9. We want to find, here's the average velocity. So remember, average velocity is equal to the slope of the, what kind of line? Secant line. So pause the video to copy this down. Find the average velocity over the time intervals t to t plus h and 3 to 4. So first we're going to work on the general derivative, or the average velocity for this. All right, so this is just going to become, we don't need a limit here with average velocity. This is just going to be f of, instead of a, I'm using t and t plus h, so we'll do t plus h minus f of t all over h. So I'm using this function up here. So then this becomes t plus h squared minus 4 times t plus h plus 9, and then minus f of t, which is just t squared minus 4t plus 9, all over h. Now go ahead and pause the video just to practice, see how well you do continuing with this problem. Remember, again, this is without the limit notation, so pause the video and continue working. So squaring the quantity t plus h, we're going to get t squared plus 2th plus h squared. Distribute the negative 4, so minus 4t minus 4h plus 9. Then we get a minus t squared plus 4t minus 9 all over h. Things should cancel here. So we've got, yes, t squares are gone, 4t's are gone, and 9's are gone. What remains we can divide by h. So now this just becomes 2t. When I divide 2th by h, h squared divided by h is just h. And then minus 4h, if I divide that by h, I just have a minus 4. So I get 2t plus h minus 4. So that is the average velocity over the time interval from t to t plus h. So now let's look at the interval from 3 to 4. Well, since I already found this, I don't have to go through this process again. Here, this is my t. This is t plus h. So what did I add to 3 to get 4? So in this case, h is just 1. And now I can substitute in here. So the interval, so the average velocity here is just going to become 2 times 3 plus 1 minus 4. So that's 6 plus 1, 7 minus 4 is 3. And let's see what we're given in here. Meters, and we'll say per second. Usually it is meters per second. So again, let me know if you guys have questions on that problem. Now let's find the instantaneous velocity when t is equal to 4. Well, we know the average velocity simplified into the 2t plus h minus 4. So then the instantaneous velocity, why go through all those steps again? It's going to still come out to be this, just with the limit as h approaches 0 in front of it. Because we already did that difference quotient formula. Why go through it again? So now this is just saying h becomes 0. So now I just get 2t minus 4. So now when t is equal to 4, this becomes 2 times 4 minus 4, 8 minus 4, which is 4 meters per second. So again, now we don't have to go through the table of values and pick values like 3 3.1, 3.8, 3.999. If we're getting closer and closer to 4 here, this is how we could just do this a lot quicker. Pause the video again to copy this down. Find an equation of the tangent line to the graph y equals h of x at x equals 2 if h of 2 is negative 1 and h prime of 2 is equal to 4. All right, so what we need the slope of the tangent line. So if you remember, the slope of the tangent line is the same thing as f prime of a. So in this case, we're actually going to use h, because instead of f of x, we're h of x. So this is going to become h prime of a. Now if you notice up here, because we're looking at x equals 2, so we want to know what h prime of 2 is, and that's given to us. So that's 4. So the slope of the tangent line is 4. Next, we need a point. And that's going to come right from here. H of 2 equals negative 1 becomes the point 2, negative 1. So we didn't have an actual function to go through that difference quotient, the definition of a derivative. We were just given little function notation here in order to test our understanding of this. The slope of the tangent line was h prime of a, and more specifically h prime of 2, which is 4. The ordered pair came from h of 2 equals negative 1. So now I could just use point slope form to write the equation. Pause the video and go ahead and do that. Remember, it's y minus y1 equals m times x minus x1. So I'm going to get y minus a negative 1 equals our slope 4 times the quantity x minus 2. So this gives me y plus 1 equals 4x minus 8, and then I get y equals 4x minus 9. So there is the equation of our tangent line. Okay, again, pause the video to copy down this problem. Again, it's not as lengthy as going through the definition of a derivative. We're not given a function here. But it does say if the tangent line to y equals f of x at 2, 1 passes through this point, negative 2, negative 4, find f of 2 and find f prime of 2. So again, we don't have a function, but what we can do is just kind of imagine plotting these points and understanding what's happening here. So if I went over 2 and up 1, here's the point 2, 1. And then I would go 2 to the left and then down 4. So here's this other point, negative 2, negative 4. So I have a line going through these 2 points. All right, now the point right here at 2, 1, that's tangent to a curve. So let's say I have some kind of curve looking like this. So here is my the point where it's tangent. So again, this is the point 2, 1. So what's blue here, this is my tangent line. So all I have to do is find the slope of this tangent line the old-fashioned way, which is just the slope formula, because I'm given another point that our tangent line goes through. So in this case, the slope of the tangent line just comes from y2 minus y1 over x2 minus x1. So this would just become, however you want to start this, I'm going to start down here, negative 4 minus 1 over negative 2 minus 2, which gives me negative 5 over negative 4, or a positive 5/4. So here we were given slightly different information. We were given 2 points the tangent line went through. So all we had to do, and again, because no matter where we're at this point here, the slope of the tangent line stays the same no matter what point we are at on the line. All right, this one's going to be a little lengthier. We have a fraction, so go ahead and copy this down. We'll work through this one together, unless you want to feel free to try this on your own. You could pause it and then continue playing. All right, so we have f prime of a, again, is the limit as h approaches 0, f of a plus h minus f of a all over h. Carefully substituting this in because we have a fraction, so we get the limit as h approaches 0. Very carefully here, we're going to get 3 times a plus h minus 2 over a plus h plus 1. That's that t plus 1 here. Minus f of a is just 3a minus 2 over a plus 1. Now all of this is over h. what do we do here? We have a very complex fraction. So let's multiply this top part. If we look at our denominators here, I need to multiply by a plus h plus 1 times a plus 1. Down here, I need to multiply by a plus h plus 1 times a plus 1. All right, so this top part, limit as h approaches 0. So what's going to happen here, when I go to multiply this LCD by this first fraction, this denominator here is going to cross out with that a plus h plus 1. I'm going to go ahead and distribute the 3, so I'll have 3a plus 3h minus 2, so that numerator will get multiplied by this a plus 1, minus, now when I go to multiply this LCD by the second fraction, the a plus 1s are going to cross out. So it's 3a minus 2 times this a plus h plus 1, but I got to be careful because I'm subtracting. I need brackets. Now all of this is over h times a plus h plus 1 times a plus 1, which we'll just leave right now. So now we have to carefully go through and distribute the limit as h approaches 0. Here I'll have 3a times a, so I'm going to get a 3a squared. 3a times 1 is plus 3a. Then I'll get a plus 3ah, multiplying 3h by a, and then plus 3h times 1. Then I'll start with the 2, minus 2a minus 2. And I still have to multiply these two quantities. So 3a times a is 3a squared. 3a times h is plus 3ah, and then plus 3a. And then we'll get, squeeze this in here, minus 2a minus 2h minus 2. All of this over h. All right, so we've got the limit as h approaches 0. I want to go ahead and distribute this negative sign here. So we have 3a squared plus 3a plus 3ah plus 3h minus 2a minus 2, and minus 3a squared minus 3ah minus 3a plus 2a plus 2h plus 2. All of this is over h. Now, hopefully we could start to cancel some things out. 3a squared minus 3a squared is gone. We have a 3a minus a 3a. We have a 3ah minus a 3ah. We have a minus 2a plus 2a. We have a minus 2 and a plus 2. So what does that leave us with? Oh, and I forgot to do this. In our denominators, I don't just have an h. I have a plus h plus 1, a plus 1. Very important. We can't forget that. A plus h plus 1, a plus 1. All right, so what's left in the numerator now? I have a 3h plus a 2h, so that's nice and short. 5h over h times the quantity a plus h plus 1 times the quantity a plus 1. All right, so yes, now these h's divide out. I'm still left with the limit as h approaches 0 of 5 over the quantity a plus h plus 1 times the quantity a plus 1. What's going to happen now? This h becomes a 0. I no longer need the limit. So 5 over, I get a plus 1 times a plus 1, so I get 5 over a plus 1 squared. All right, so we were asked to find f prime of a, and we did that. F prime of a. All right, our last example kind of gives things in reverse. We have to pull the function out from each description here. So each limit represents the derivative of some function at some number a. State such a function and a. So we're going back to the limit, this notation here, as h approaches 0 of f of a plus h minus f of a all over h. So where we get to answer the first part of the function comes from this right here. So this is really our f of x, but the a is already substituted in. So go ahead and copy down example a. And what we're looking at here is we go to this part right here. This tells me that f of x is really equal to sine of some value here. The specific value is a pi over 4. A generic value is just x. So f of x is equal to sine x. A is what's already in there. A is the pi over 4. So that's all we're trying to do. Now that's a pretty straightforward example. This next one here for b, again, pause the video to copy this down. All right, here we're just given a number, so we need this help here. What this is really looking at, this is using the limit, and I shouldn't have an h there, that should be an x, because it's using that other version that I wrote down. So what this is using here is the limit as x approaches a of f of x minus f of a over x minus a. So this is a little bit easier to say, well, hey, a is 2 right here. And now this part, not the 16, this part here, this is f of x. So f of x is equal to 2 to the x. And that should have actually been a 4 there if x was 2. Let me change that there. All right, so let me go back over that one with you, rewrite it again. So if I had 2 to the x minus 4 over x minus 2. So again, in this case, a is 2 here, and our function is 2 to the x. And that 4, that should make sense because that should be 2 to the second there, which is 4. All right, this next one again involves h in our denominator. So again, we're kind of using a combination here. If this was already calculated for us, but if we go back here, remember this is just a plus h squared, which is really going in for this part here. So our function is really just going to be an x squared. And then a was this value that's going in for a plus h. So a is 3. And this makes sense over here because this is just 3 squared. And then d still looks a little different. We're just looking at a function here. Usually what's happening is this last part is it's already calculated, and then typically this first part, so go ahead and pause the video and copy it down before I continue explaining. So this last number can kind of stand alone because this is looking at that f of a is already calculated. So again here, a is going to be, this is as t is approaching a. So right now we know that a is 7. So when we see this last number here, we know that 7 just got substituted into what? And chances are it's just going to be those first two. Because if I try this, 2 times 7 squared is 49. 2 times that is 98. And then this is 35, and 98 minus 35 will give me 63. So here my function, in this case f of t, is just equal to 2t squared minus 5t. And a is a special t value, which is 7. All right, so a lot of information going through section 2.1 here, but please take your time to revisit these problems and let me know what questions you guys have.